Thank you, Simone. Thank you, Stan, for the invitation. And I intended to apologize because I was supposed to run away soon after my talk, but I had an information, a last-minute information. This is actually not true. I will remain until 2:30, and I apologize with the following speakers. This is a perspective talk. I feel that this is also a premise that I have to make, and the perspective is on the discussion that the International Association of Hydrological Sciences engaged to identify the topic of the next science initiative of IHS for the decade 2013-2022. This will be the follow-up of PUB, the Prediction in Angojan Basin Initiative, which we all know it was very much successful. More or less 500 papers made reference to PUB already. So IHS is conscious that this is an important issue to identify the topic for the new decade, and they opened a discussion. The discussion is taking place through physical meeting, but above all is taking place through a blog, which you see a snapshot here. And this is the web address of the blog. Please consider the opportunity to contribute, especially young scientists. IHS appreciates very much your opinion. And the discussion is open until September, so there is time. But it's really very much important that people from the community contribute to this discussion. The keywords so far, this is not a comprehensive list, are change, society, uncertainty, historical, comparative hydrology, and coevolution. And I'm going now to give a brief perspective on this keyword by summarizing the discussion that is taking place on the blog and by providing some personal interpretation. So, change is on the plate, as Thorsten said in one of his talks during the week. And change, in order to understand what we mean in a practical view, let's have a look at this picture that Hanna Sikorska kindly gave to me. It was taken in Warsaw around 1995, and 15 years later, the situation is like so. You see, the world is still there, but it's the only thing that we can recognize from the previous picture. So, of course, this is affecting very much the environment, the water cycle, but there is also feedback, because we have to be concerned to give water to these people, and therefore water exploitation becomes an issue. And there are other reasons for change, of course, that we well know, and like groundwater exploitation, irrigation, and you make it as complex as you wish by incorporating all the interactions between humans and the water cycle. And another good example of interaction between human, society, and water cycle was given by Giuliano Di Baldassare during his award lecture during the week. This is a study that investigated the flood fatalities, the progress in Africa during the last decades. You see a dramatic increase here. And the increase was caused by migration. Migration from to the cities, close to rivers, and therefore people got more exposed to floods. And in fact, you can see that the fatalities, the floods occur in the area where population growth was more significant. This is another excellent case of what the new decade should study, this kind of interaction. I wanted to inspect with a little bit more details this interaction between human and society, and therefore I made some statistics on the data that the FAO makes available about the water resource consistency of each country, many countries around the world, and economical indicators. Sorry, I was too late, I skipped the slides in my speech. What we need is to include the interaction between humans and hydrology with a full integration, where with full we intend to model both ways, both the two ways of the interaction, human on water and water on humans. And I think that a key concept is the one that many authors emphasized. Among them, there is an S paper by Stoyanis and others. Water is becoming a limiting factor to societal development. And as I said before, I made some statistics in order to investigate this linkage between society and water. So let's look at these statistics. You see here a graph where here you see the total density of renewable water resources it is expressed in cubic meters over square meters, and on the vertical axis you see the Human Development Index, computed by FAO. It's basically a function of the gross domestic product plus other two indicators of societal development. And here the size of the symbols is proportional to the total population of each country. In red I just highlighted some relevant countries, and you see here that the lower right part of the graph is empty. This means that water availability is a sufficient condition to a good Human Development Index. So countries with more water are more likely to have a good development. And an interesting thing is, an interesting development of this graph can be obtained if we draw the size of these symbols not proportional to total population, but proportional to the agricultural contribution to the gross domestic product. And the graph that we get is this one. Here we use the log scale now, but again we have renewable water resources available here, and the Human Development Index here, and the size of the point is proportional to the agricultural contribution. And you see that countries with the higher water resources availability have more chances to have an agricultural contribution that is in a good shape. And finally, another graph that I wanted to show to you now shows the population density here on the horizontal axis, and again the total density of freshwater availability on the vertical axis. And here I draw, with the blue line on the right, a kind of a lower limit. You see that all the countries are above this limit, and here with the blue line on the left, I just wanted to summarize the situation of Italy. And if we make reference now to the projected population for the year 2050 by FAO, you see that many countries cross the lower limit. This means that these countries that are located in the East and in Africa will experience conditions of more severe water scarcity in the future. And therefore they will experience a water crisis, which is, as Siva said in one of his talks, a water for food crisis. So these are the kind of links that we have to explore, and also there is the concept of climate change. Climate change, we all know that we are experiencing global warming, which causes a decrease of the extension of the ice cap, and global warming may be caused by the increasing solar activity or increasing CO2 concentration, but nevertheless what it counts for us is that global warming is there and is changing the distribution of water resources, especially for some countries. So, how to model change now? This is the issue, because of course change is on the plate, but how can we model it? What is change? Change implies non-stationarity. Non-stationarity is defined as a change of the statistics of the stochastic process we are focusing on. And therefore, if we want to model non-stationarity, if we want to model change, we need to quantify how these future statistics will behave. This is a challenging question, of course, and in my opinion is also exciting, because we don't have the solution, otherwise it wouldn't be exciting, but we have the means, we have some ideas to bring forward to decipher how these statistics of hydrology will behave in the future. And I think that we must do more than scenarios analysis. What we did in the past is basically scenario analysis. We took projections of climate change, projections of future catchment behaviors, and we ran a hydrological model calibrated in reference with current conditions to try to predict the future behavior. This approach, which was useful, proved to be subjected to a high level of uncertainty, and also makes reference to a future ideal situation. I think we have to change the paradigm. We have to refer to the present situation and project it into the future. Take the present and project it into the future. This means that you analyze the current systems and investigate what kind of pressure the system in the current condition can sustain in the future. This has the great advantage of providing a reply to current problems. So, two possibilities to do this. A first possibility is to identify constraints and limiting behaviors. We have seen that water is going to be a limit to future development. A second possibility is coevolution, which means joint modeling of hydrology and related processes like catchment shaping. let now me give a more detailed perspective. My feeling, convolution is necessary if we want to improve our understanding. We have to study not just hydrology, hydrology plus the rest. From an operational point of view, this means that our model becomes more complicated, and therefore this is a concern for the technical application, because we have to decipher the linkages between hydrology and the related processes, and these links will be subjected to an uncertain representation. So this means that the uncertainty of the system will increase, and therefore for the practical application we have to be aware that this could require a long way ahead. If we are interested in technical application, probably it's better to focus on the limiting behaviors, and these constraints that I mentioned before are probably the key, are probably what we need to investigate. And I think that a considerable opportunity is given by trading space for time, comparative hydrology. If we look at the present, if we move in different locations, we can compare how similar catchments behave in different climates, and therefore we can infer how they may behave in the future. Again, look at the present. There is the need to broaden the view to an extended set of catchments. This was highlighted by main contributors to the blog. Look at the present, but also at the past, because historical hydrology is also the key. Now, let me give an example. This is a study that we performed in Italy, in central Italy, where we tried to investigate how the statistics of the river flows depend on catchment behaviors and climatic behaviors. This is a case of comparative hydrology, because we compared the behavior of different catchments in a region, but it's also rooted in regionalization and therefore classical hydrology. And I think this is another key concept. We have to project our view in the future by also looking at the past, taking classical hydrology into account. We have to bridge our history in a continuous development with a steady pace. And what we found here, we found indeed very good results. Look at, this is validation. This is a mean of the river flow, the long-term mean that was reproduced depending on catchment behavior. You see that in validation we indeed got quite good results, and the same good results were obtained for the standard deviation of the river flows and also for the memory structure. This is the lag1 autocorrelation coefficient. And if we were able to infer these statistics, then we can parameterize our model on the basis of the statistics, not the hydrograph. And to do so, this is my personal feeling, but I'm biased in this, I think that spectral calibration is an opportunity, because it's a way to calibrate the model by taking the statistics into account, and also it's a way to inspect how systems behave and change at different time scales. So we can identify what are the time scales that are subjected to change. So I think it's indeed an opportunity which is also easier than what this equation suggests, because indeed spectral calibration is almost finished. Is indeed not really so complicated. These are my conclusions, which I leave to you to read, because basically they are a summary of what I said. I just would like to conclude with an auspice. I really hope that the new hydrological decade, the new HS decade, is inclusive with respect to the community and exciting. And please, the blog, contribute on the blog. Thank you.